Hello everyone, this is Fuxun. Today I'm glad to share our new work, SC-UDA style and content gaps aware unsupervised domain adaptation for object detection. This is joint work from George Mason, Microsoft, and Wayne State University. Our work aims to address the unsupervised domain adaptation problem. So given the source domain with labels, what we want to do is to adapt the detector trained on source domain to the test on target domain and get optimal performance. There are many challenges in the unsupervised domain adaptation. The most obvious phenomenon is that there are many domain gaps that are causing the performance degradation when we are transferred from the source domain to target domain. And previous work have characterized many domain gaps that are causing the accuracy degradation. For example, the style gap is one commonly known gap, which means the various textures, colors, and the environmental lightings that are influencing the accuracy when you transfer from source to target. However, there is another gap, what we identify as content gap, that are also affecting the accuracy. For example, we show an instance density distribution from KT and to cityscape datasets. You can see that the density distribution for these two datasets are different, and KT images are usually having more sparse objects, and in the target domain cityscapes, you can observe that there are usually more objects, and this kind of density distribution can also influence accuracy, since you have never seen such dense scenarios in your source domain. So the accuracy when you transfer will also be influenced. So these two gaps are what we considered as major factors that are affecting the accuracy. So we conduct a lot of case studies that showing that these two gaps are the critical factor in domain adaptation. The first case study is we using 3 training datasets and test on the cityscape. The first one is the original cityscape, that means no domain gap. The second one is the random stylized cityscape, so we change the styles of the source images so that we introduce the style gap. And the last one is the stylized SIM10K, which we introduce both the style gap and content gap. So you can see that the performance of these 3 datasets are continuously degrading, implying the influence of style gap and content gaps. For content gap alone, we also tried to use to sample different distribution, but using the same images from the cityscape. You can see with the same number, but only differs in the distribution. The two datasets also show a significant performance degradation that shows the influence of content gap. So these two case studies shows that both style gap and content gap are the major factors that are affecting the domain adaptation performance. So what we do is to combine and resolve these two domain gaps to achieve optimal performance in domain adaptation. So to solve the style gap, we propose the fine-grained CycleGAN. CycleGAN is a widely used style translation tool that have been proposed before. However, we found for object detection tasks, previous CycleGAN usually have a large reception field, and it tends to change the backgrounds and the details too much, so which is pretty bad for object detection adaptation. So we use the small reception field regulation, and thus proposed the fine-grained style translation by CycleGAN. And you can see, as this table shows, with finer reception field, we actually get increasing domain adaptation performance. And for the content gaps, we also propose the self-training with pseudo-labels. So the basic idea is to use a pre-trained detector on the source domain to label the target domain with pseudo-labels. And then we can use these pseudo-labels to self-training and continuously improve the detector itself. So we also propose imbalanced sampling and confidence thresholding to select and filter out wrong pseudo-labels. And both these strategies, solving the style gap and content gap, have shown great performance in our experiments. So on 3 common benchmarks, our work could achieve 18%, almost 18% MAP than previous baseline, and we also achieved 3 to 6 point MAP improvement than previous SOTA. Yeah, thank you very much. For more details, you can reference to our new paper. Thank you.